Good morning. My name is Max Midwinter, and I'm presenting the paper titled Explainable Machine Learning for Seismic Vulnerability Assessment of Low-Rise Reinforced Concrete Buildings by myself and my co-authors, Dr. Yum and Dr. Kim of the Civil Engineering Department at the University of Waterloo. I'll start off by speaking a little bit about the background and to motivate the work. Then we will discuss a bit about the machine learning particulars and the complementary machine learning explainability method. Then I'll talk a little bit about our experiments and our results. Finally, I'll conclude the presentation with our next steps and future work. The priority index was proposed by Hassan Chosen in 1997 and was designed to be a rapid seismic vulnerability assessment method for low-rise reinforced concrete structures, where the PI is inversely related to the structural damage. The PI is calculated from equations 1 through 3 using the structure's features, such as the area of the columns, total floor area, concrete wall area, and masonry wall area. In total, they require the inspector to collect 7 structural parameters, which can be done via structural drawings if they are available. On the right-hand side is a plot of the Hassan Chosen PI index in the original paper. The boundary lines are determined by the engineer for a specific region to best separate the damage classification space. The Hassan Index has become a very popular method for post-earthquake reconnaissance teams who have collected numerous records from different earthquakes, and they have shared their results on Data Center Hub. DataCenterHub.org, hosted by DEEDS, Digital Environment for Enabling Data-Driven Science, is funded by the National Science Foundation. Using the original PI method, we've created the plots for the various earthquake events. The x-axis is the wall index, and the y-axis is the column index. The blue, orange, green, and red dots represent no damage, light damage, moderate damage, and severe damage respectively. According to Hassan Chosen, ideally we like to see the red dots at the bottom left corner and the blue dots at the top right corner. But as you can see, the separation is less than ideal. So how good is it? Drawing thresholds is analogous to logistic regression on a 1D array, the priority index. So we'll use Python and scikit-learn to save us the headache. This will be used as a baseline to compare our methodology. As expected, the results are not so good. It's almost twice as good as randomly guessing, but take it with a grain of salt, because what you don't see is the class distribution, i.e., if you have mainly severe damage classes, and if you draw a boundary line really far out, you can get 0 recall on all the other classes and still get good results. For the sake of argument, let's just call these accuracies our benchmark. So what are the pros and cons of the priority index? The pro is it uses easily collectible data, and it's intuitive to understand. However, as we demonstrated in the slide before, it has low real-world accuracy. At the risk of sounding like a TV salesman, how do we get all the pros of PI without any of the cons? This leads us to our objective. Design an explainable model using easily collectible data that exceeds the performance of the Hassan Priority Index for rapid structural evaluation. As you probably gathered from the title, we'll be using machine learning. Consider we wish to create a dogs and cat classifier. We have 3 distinct features which create a basis, and each dog and cat occupies a point in the vector space. In 3D, using 3 features, we require a plane to separate the dogs and cats. In 2D, if we remove one feature, we require a line, and in 1D, just a point. It can be seen that as we reduce the number of dimensions, dogs and cats become less separable, but the number of parameters to create the threshold to separate dogs and cats decreases. This is analogous to Hassan Priority Index, which reduces the number of parameters from 7 to 1. To make it more simple for humans to understand and utilize. However, this simplicity for humans makes the data less separable. Machine learning algorithms, on the other hand, are able to best leverage the number of records in the data to automatically fit complex models, which may be better at prediction tasks. Machine learning algorithms, though, generally use a lot of data. The reason for this is the curse of dimensionality. Imagine each feature is a basis, and each record is a point in the vector space. The more dimensions you have, the easier it would be to separate the different records. However, what you don't want to happen is picture 3 of our dogs and cats example, where each case is an edge case and the model fails to generalize on the training data. This is called overfitting. As we increase the number of features in our model, so we have to exponentially increase the number of records that we have. Lastly, machine learning is a bit like a black box. Unlike the Hassan index, which uses equations 1 through 3, which are very intuitive, the machine learning model can be very complex that is impossible to understand without aid. How do we overcome these challenges? Firstly, we use SVM-SMOTE, which stands for Support Vector Machine Synthetic Minority Oversampling Technique. This is used for imbalanced class labels. Specifically, it uses SVMs to choose which minority samples to create synthetic labels of. Then we use a random forest classification model, which is a popular ensemble learning method based on classification and regression trees. These random forest models usually give us high accuracy and they have a low overfitting risk. We use k-fold cross-validation, which is a resampling procedure used to evaluate machine learning models. Finally, we use SHAP, which stands for Shapley Additive Explanations, which provides additional insight about how machine learning models make decisions. This is based on the Shapley value, which comes from game theory. Imagine a group project, and there was some function v that allows you to calculate your final grade based on each group member's contributions. N is the set of all group members, S is an arbitrary subset of group members, and I is a person in the group. Then the Shapley value phi I for group member I is given in equation 4, where phi I is the weighted average marginal contribution of a group member I calculated for every possible subset of members. The Shapley value is attractive for explaining complex models due to its conformity to the axioms of efficiency, symmetry, dummy player, and additivity. Continuing with the group project analogy, group members who do the same work receive the same grade. A group member who does nothing receives 0, and the contribution of each member is additive to the whole. Calculating the Shapley values are very expensive since you need to calculate the marginal contribution for every combination of subset features. SHAP is a library created by Lumberg et al. For model explainability, which estimates the Shapley value. In this work, we use TreeShap, which specifically optimized to work with tree models like random forest. Now let's look at Taiwan. We created a model with all the features that we would use to calculate PI into our random forest model. Our model outperformed PI by 8.7%. We can use SHAP now to create a summary plot like so. The graph ranks how important a feature is to the model making decisions for each damaged class. We notice something strange, and that is concrete walls are less important than masonry walls. This is very counterintuitive. Case 2 and 3 are when we split the dataset based on structures with concrete walls and those without concrete walls. Subsequently, their SHAP values are shown. In case 2, masonry walls have the lowest influence, and in case 3, concrete walls have no influence because they don't exist. And in SHAP abides by the dummy axiom of Shapley, which dictates that features that do not contribute to the prediction will have a 0 value. Finally, we can use this plot as a PCA analysis. We can identify that we can probably remove masonry walls east-west and masonry wall north-south from our model for concrete walls. When we remove some features, we observe that our accuracies increase. This is likely due to the curse of dimensionality as we discussed prior. For Ecuador, we have some additional data, including whether the structure had eccentricities, soft stories, or captive columns. We decide to include these features into our model to see if we can get better accuracies. We use Ecuador because Ecuador had roughly balanced classes, and all the structures do not have concrete walls. Additionally, it is a relatively large data set at 171 records, which means we don't have to worry about the curse of dimensionality as much. Like for Taiwan, we trained a model. As we can see from the table, when we incorporate these additional features on a reduced model, this model outperforms the baseline, which means that there are other easily collectible structural features that are better than those in PI. Lastly, I want to show the dependence plots that we can produce with SHAP. This step would be much better once we have a high fidelity model. That way we can use those trends to gain an understanding of how the model is working. In this case, we notice the formation of some clusters, where the pink clusters are for taller structures and blue clusters are for shorter structures. In general, we see that taller structures are more likely to be damaged compared to shorter structures. I want to iterate that we will need better models and better data to really create nice looking plots. We do have plans to do something about this in the future, using numerical simulations to fill in the blanks. So what are our next steps? We are in the process of seeking out more data, either from different earthquakes or more information about existing earthquakes. We are looking for similar data sets that have different structural parameters. We are looking to use numerical simulation to supplement our existing data sets. We are looking for a measure of seismicity to connect the different earthquake events together. Hopefully, this will allow us to create a universal seismic vulnerability model. Thank you for coming to my presentation.